In this video, I'm going to be describing how we can use the first and second derivative tests to describe behavior of a graph. Let's review what we know about our first and second derivative tests. We know that if the first derivative is positive, our slope is positive, so our graph is increasing on that interval. If our first derivative is negative, that means our slope is negative, which means our graph is decreasing on that interval. If our second derivative is positive, we know our graph is concave up, and if our second derivative is negative, we know our graph is concave down. We can combine these in a lot of different ways. For example, if I know that my first derivative was negative but my second derivative was positive, I would know that my graph was decreasing but concave up on that interval. Another way we can combine our first and second derivative tests is to figure out what type of extreme we have. So we know that if our first derivative changes from negative to positive, we reached a minimum, but we can also say that if we have a zero of our first derivative and our second derivative is positive, we've reached a horizontal tangent line or some extrema where our graph is concave up, which also tells us that we had a minimum. And likewise, if we knew that our first derivative changed from positive to negative, we reached a maximum, but we could also say that if we found zeros of the first derivative and our second derivative was negative, we reached extrema where our graph was concave down. So we also could use that method to determine that we reached a maximum. If your first derivative is zero, or you find zeros of your first derivative, and the second derivative is also zero or undefined, our second derivative test fails and we've got to rely on the first derivative test. So that occurs when some functions are not differentiable beyond their first or second derivative. Let's do an example and use the first and second derivative test to really visualize the behavior of this graph. So we'll use the example x to the fourth minus 4x cubed. Let's find the first derivative and describe where our graph is increasing or decreasing. So find the first derivative of this function using the power rule, and then find zeros or critical points of the first derivative. And we find our critical points happen at 0 and 3. So we can set up our intervals around those critical points and test values on the interval to determine where our graph is increasing or decreasing. So in the first interval from negative infinity to 0, I'm going to test -1 and plug it into the first derivative and evaluate it. I don't necessarily need to know the value, although you could. You just really need to know whether it's positive or negative. So if I plug in -1, I get a negative solution anywhere on this interval. I know that my graph is decreasing on that interval. If I plug in a value that's in between 0 and 3 for the second interval, I get values that are negative. So I know that my graph is still decreasing. And if I plug in values for this third interval, for example, 4 would be a number on this interval, and plug it into my first derivative, I get positive values, which tells me that my graph is increasing. So my graph is decreasing from negative infinity all the way up to 3 before it starts to increase. And right there, where I changed from a negative first derivative to a positive first derivative, or I went from decreasing to increasing, I must have reached a minimum. So we reached a minimum at x equals 3. Let's figure out what we can tell by our second derivative test, and then we'll combine the two. So we'll find the second derivative of the original function by finding the derivative of the first derivative. So derive that again, and we get the second derivative. We'll set it equal to 0 and find possible inflection points. Again, we don't know that they're inflection points until we do our test and determine that we actually changed concavity. So finding zeros of the second derivative, we get 0 and 2. Use that to set up our intervals. So from negative infinity to 0, if I plug in any value on that interval and plug it into my second derivative, I get positive values telling me that my graph is concave up. Plugging in values on this middle interval from 0 to 2, such as 1, I get negative values for my second derivative, telling me that my original graph is concave down. And in testing my third interval, I can plug in a value like 3 into my second derivative, And I can tell that I'm getting positive values out of that interval, so my graph is concave up. So I know that my graph is changing concavity at 0 and 2, so those are our inflection points. And I know that my graph is concave up from negative infinity to 0 and from 2 to infinity. And my graph is concave down on the interval from 0 to 2. So let's combine all of that information into one visual. I like to use a little number line. I'm going to combine my intervals. So using my critical points and my inflection points, I'm going to set up all of these intervals. So from negative infinity to 0, from 0 to 2, from 2 to 3, and from 3 to positive infinity. And then I'm going to describe all of the information that I found from my tests. So I knew that on the interval from negative infinity to 0, my first derivative was negative, my second derivative was positive, so that I know that my graph is decreasing and concave up on that interval. Then on the interval from 0 to 2, I know that my first derivative was negative and my second derivative was negative, so my graph is decreasing and concave down on that interval. From 2 to 3, I got my first derivative was negative and my second derivative was positive, so I know that my graph is decreasing but concave up. And then on my last interval from 3 to positive infinity, my first derivative was positive, my second derivative was positive, so that my graph is increasing and concave up on that interval. So we can summarize all of that information and sketch the graph out, and we know what our graph looks like without having to look at it on a graphing calculator. So I knew that on my interval from negative infinity to 0, my graph was concave up but decreasing. So concave up but decreasing. And then at 0, I had an inflection point, so I changed concavity, but I still was decreasing. So I changed to concave down but still decreasing. And then at 2, I had another inflection point. So even though my graph still was decreasing, I changed to concave up. And then at 3, I reached my minimum. So my graph changed from decreasing to increasing. And my graph was also concave up and increasing from 3 to infinity. So we got all of the information about our graph by using our first and second derivative tests.